Okay, so let's take a look at today's lesson. This is our second lesson in our unit for three-dimensional vectors. We're going to be looking at projections of vectors today. So this unit, I wrote this unit, I designed this unit to help us in preparation for multivariable calculus. And after teaching multivariable calculus, I noticed there really isn't a lot of, we didn't have a lot of three-dimensional vector stuff. And so this is just really a help. So that we can kind of get a better idea of what's going on, just like a little preview. It's at least some information, some knowledge about some three-dimensional things. So today we're going to look at projections of vectors, and that concept can be a little bit difficult, so I'm going to try to explain it to you like visually first. We're going to talk about what is it. Basically, we are not required to write a vector with respect to the x, y, or z axis. We can put a vector anywhere we want. I mean, I think you can think about that, right? We can write a vector anywhere we want. And a projection of one vector on another, I like to think of it like it's a shadow. If you think of it like a shadow. So kind of visualize maybe for this vector right here, maybe the sun is straight above. And the sun would be shining on this vector A. And this would be like the shadow of that vector, right? So that's a vector projection. It's projecting itself orthogonally onto another vector. It's called the, this particular formula is the scalar projection of vector A onto vector B. So a scalar is a number. We're looking for a number. And the scalar projection of vector A, so it's projecting onto vector B. Notice how at the terminal end of A, we're dropping a perpendicular line to this vector, vector B. We're not, perpendicular to the x-axis or y-axis. It's one vector to another. And so what that scalar projection is, it's the length of the projection. So it's the magnitude. It's this length of the projection. And it's calculated by this formula. So S stands for scalar projection. Scalar projection. So we would take the magnitude of this vector, vector A, and we would multiply it by cosine of the angle between the two vectors. Okay, that's how we would get this scalar projection. So that's just a number. And this is just a formula right here. Now there will be times where we don't have the angle measure. We have two vectors, but we don't have the angle measure. The vectors are typically going to be already, tail to tail. We should remember, hopefully from the last unit, we can find the angle between two vectors, right, as long as they're tail to tail. And that was this formula. So there will be times where we have to actually find the angle measure. We're not given the angle measure. And we would simply use this formula from the last unit to find this angle measure. Okay? So this formula calculates for us the scalar projection of vector A onto vector B. These two formulas basically go hand in hand. They're a pair. To do the vector projection of a vector A onto vector B, which is what we're looking at here, we're projecting vector A onto vector B. It's the orthogonal projection, so notice it's orthogonal, or in other words, perpendicular, that forms a right angle. So it's orthogonal projection, as is this, of A onto B. And it's this formula. This S is this. Okay, these formulas work together. All right, S is magnitude A cosine theta. That's what the S is. So what do we do to turn it into a vector? So a scalar projection is a number, and a vector projection is a vector. So we take our scalar projection, and we're basically multiplying it by the vector that we're projecting onto. We're projecting onto B, so we're using vector B. So this hopefully looks familiar. B over magnitude B. We recognize that. What is that? B over magnitude B. Wasn't that normalizing? Remember normalizing from the last unit? This is a unit vector. Okay, in the direction of B. It's not like I, J, or K. It's actual own unit vector in the direction of B. So this is a dual formula. These two work together. And what I'm trying to do is explain what you're doing. I know that's kind of complex. Really, the mechanics of what you're doing are all going to be by formula. You just need to know how to use the formulas. Okay, it's just and on the quiz, I'm going to write these formulas on the quiz. I'm not going to tell you what they are or how to use them, but I will have these formulas, your scalar projection formula and your vector projection formula, written at the top of the quiz. Okay, so that you can access to them. You don't have to memorize these formulas, but you do have to know what they are and how to use them. All right, so these two go together. Those two formulas are hand in hand. There is another formula that we're going to learn, and when we use this particular formula, the third formula, I will tell you to do that one. Our standard one is the first two. These are the formulas that we learn in Precal. Okay, so these are Precal formulas. There is a third formula that we learn in calculus, this formula, and it also does an orthogonal projection. But in this particular case, you don't have to know what the angle measure is to be able to do this orthogonal projection. Okay, and I will put in the directions when you use it. I'll use this notation right here. This is the projection of A onto B. Hopefully notice how it looks like A is projected onto B. Hopefully that'll help you get the order right. If we're projecting onto B, we're using a lot of B information, right? So this particular formula is a different way to calculate the orthogonal projection of A onto B. This is vocabulary words, orthogonal projection of A onto B. And this is without finding the angle between. We would use this formula. So what would we do? We would do the dot product, A dot B. Okay, we do the dot product of those. And then see how it's kind of like this part of this formula. So we would do the dot product, and we would divide the dot product by the magnitude of B squared times the vector B. Okay, and that would get us our projection. So this is an alternate formula. Again, I'm not going to require you to memorize it. I'll write it on the paper, and I will indicate when to use that formula by using this exact kind of notation. That will tell you when to use that formula. Otherwise, we're going to be using these two formulas. Okay, these are our main formulas. I just wanted to show you there is a different way and get you kind of familiar with calculating it. All right, questions on the formulas themselves? All right, let's go to the next slide then, and let's work a few examples. All right, so our first example, we have vector B. We're given vector B, and we're told that vector A is 10 units long at an angle of 70 degrees to vector B. Okay, great. So they want us to find P, which they are saying is the vector projection of A onto B. So A onto B. That's what we're looking at. We're finding vector P. In order to do that, we need the formula. So let's just kind of write the formula. So I'm going to combine those two formulas from the previous page into one formula, the scalar projection times the vector projection. So that was, we would do the magnitude of A, because that's the one that's A is projecting onto B, cosine of theta, and theta is 70 degrees. Then we multiply that by vector B over magnitude of vector B. All right, that's the formula that we're going to use. Okay, so let's do that. So this is going to be, so the magnitude of A, we're told, is 10. We already have that, right? The magnitude is 10. So it's 10 cosine 70 degrees times vector B is 8i minus 5j plus 3k, and that would be over the magnitude of B. So let's just do a little scratch work up here and find the magnitude. So it'd be 8 squared plus negative 5 squared plus 3 squared, right? That's our magnitude. And I would have a calculator, so I find that, and that turns out to be the square root of 98. Okay, so that's the parts of the formula that I need to calculate my vector projection. Now this is this is a lot of calculations. Basically, this is some weird number, right? We're going to have to take this number. I went ahead and found it. It's like 3.4202, etc. We would keep it in our calculator. We don't want to round anything. I'm multiplying that times 8. Let's get this written up here. So to get my I component, I would have to multiply this vector times 8 and divide by root 98. Right? You with me on the calculations? I would do the 3.4 times the 8, divide by root 98. And that would give me 2.76, etc. So I'm going to round to the thousandths as our norm. So that vector is 2.764 I. So there's my horizontal piece, the I. Let's look at the Y component. So I would multiply the 3.4 times the negative 5, divide by root 98. And that's going to give me negative 1.727 J. And then lastly, we'll work on the Z component. I would multiply the 3.4 times the 3, divide by root 98. And that would give me a positive 1.036 K. And those are the components of my new vector, the vector projection of A onto B. We okay with that? Okay, so basically it's the formula. We just need to know how to use the formulas and with our calculator. All right. So question number 2, we have vector A and vector B, and we're asked to find the scalar projection and the vector projection, but notice there's something missing there. We don't have the angle measure. We do not have the angle measure. Okay. So we need to get the angle measure. We need to use the formula that we learned in the last unit, which I won't give you this formula. You should know this formula. Right, it's cosine theta equals, remember it was A dot B in the numerator. So negative 4 times 6 is negative 24. 5 times negative 8 is negative 40. 9 times 1 is 9. So we would have a calculator. We would, combine those together. And then our magnitude, remember it was the magnitude of A times the magnitude of B. Are we pretty comfortable with magnitudes? I don't need to go through those steps, right? We know how to do the magnitude. So I'm just going to go ahead and straight write those up there. So these were the magnitude of A and B. One of them is, let's see, the square root of 122. The other one is the square root of 101. And so we would have our calculator and we would enter this number, right? And then we would do inverse cosine. This is just a review. Right? We know an inverse cosine, that would give us our angle measure. So theta, when we do that with our calculator, theta turns out to be 119.7011. We would keep that angle in our calculator stored. All right, so now we know the angle measure. We can use our formula. First, we want the scalar projection, right? That was the magnitude, and we're projecting A onto B. So we need the magnitude of A, and P, we're just going to say that's the scalar projection. There's no vector sign over it. It's just a scalar projection. So the magnitude of A was the root 122. And then it's cosine of that angle we found, cosine of 119.701, etc. So we have all that in our calculator, and we discover that the scalar projection is negative 5.47, and I'm going to round to the thousandths 3. I'm rounding to the thousandths for my answer, but I wouldn't round when I go into this because I need this number to do the vector projection, right? I need that number. So I would store this in my calculator. In fact, notice how this number we're having to distribute 3 different times, this scalar projection. It would be handy if you stored it like as A, so you could just do A times, each one of those things instead of having to, scroll up and pull this number down 3 different times. Just an idea that you might want to do. So now let's work on the vector projection. So here's my scalar projection, the negative 5.47 4, 7, blah, blah, blah. I'm multiplying that by vector b, which is 6i minus 8j plus k, over its magnitude, and its magnitude was the root 101. Now it's just a calculator exercise. I'm going to have to distribute this times the 6 and divide it by 101. This times the negative 8 divided by 101, root 101. You with me? This times the 1 divided by root 101. I just have to do all that calculations with my calculator. And then I would come up with the vector projection P. And I'm going to round to the thousandths, is negative, the first one, the I component, negative 3.273 I. The second one is the J component is plus 4.356. And the third component, the K component, will be negative 0.545. Okay. And there's my vector projection of A onto B. Are we okay with that? Okay. So those are the formulas we're going to use the most. I do want to just kind of give you a glimpse of this other formula. And in calculus, when we use this other formula, there are a lot of other things that we do. It's not just like find the vector and we're done. So I'm just going to say there's a lot of other things that we do after this formula and with this formula. We're just going to use the formula. So the formula is that PROJ, they're projecting V onto B, because that's what they're wanting us to do, project V onto B. And that formula is V dot B over magnitude B squared times vector B. Of course, these are all vectors. So that's the formula you would use when I indicate to use that formula, just for practice. So with this particular formula, we do not need to know the angle between those two vectors. We don't need to know it. It's not in the formula. The formula compensates for it. So we're going to do V, just do V dot B. So 2 times 1 is 2, plus 2 times 1 is 2, plus 0 times 1 is 0. So my dot product is 4. Okay. Now let's work on the magnitude of B squared. So B would be 2 squared plus, yeah, we're doing the magnitude of B. So magnitude of B would be 2 squared plus 2 squared. So that would be 2 squared plus 2 squared, 4 plus 4, and the square, basically it would be 8 square root of 8, and that's squared, so it's just 8. Okay, so that's our magnitude of B squared. So you see what's happening? It's basically just negating the root. Right, squaring a magnitude is just kind of negating the square root. So let's use our formula. So V dot B was 4, magnitude B squared was 8, and then we multiply it by vector B, which is 2i plus 2j, and then we distribute the scalar, and we get our vector projection is I plus j. Okay, and so that's that kind of a formula. I do want to go back to the other slide, and it just occurred to me I forgot to mention, so let me go back to the other slide for just a moment. Are we okay with these examples? Okay, let's just scoot back just for a second. I need to point something out visually to you. Come on. There we go. And that is about vector projections. So let's look at this example right here. When I was talking to you about a shadow projecting a vector onto another vector, see how these vectors are going the same way? That's not the only way you can project. You can also project, let's kind of think about it as backwards. Notice how we're projecting vector A onto B, but A is this angle measure is greater than 90 degrees. Okay, that's okay. I just want you to know that's okay to project backwards. So our projection would be back here instead of up here. Okay, and the formulas compensate for it. I just want you to know that's okay. Okay? All right.